Hi everybody, this is Mr. Fowley again. Sorry about, oops, I just misspelled my name. This is 5.3b, so we are going to hop right back into it. Sorry about the problem with that. And let's see if we can go fairly quickly through this. So, sorry if I teased you by giving you the idea that this is going to be 9 minutes long and that's it. Zinc metal is added to hydrochloric acid to generate hydrogen gases and is collected over a liquid whose vapor pressure is the same as, this says water, which says 18 torr. The volume of the mixture is 1.7 liters and the total pressure is 0.810. This is atmospheres, this is torr, that's bad. So the first thing I'm going to do is, when I collect it over water, if it's collected over a liquid, I have to use Dalton's law of partial pressure and subtract off that pressure. So that means I have to have 0.810 atmospheres minus 18 torr. Now, of course, 18 torr is the wrong unit, so I'm going to convert 18 torr into atmospheres because that's my PV equals nRT friendly equation. I gave you this way back in an earlier podcast, but 760 torr equals 1 atmosphere. So let's figure out how many atmospheres that is. 18 divided by 760 is a piddly 0.0237 atmospheres. So, 14. Determine the number of moles of hydrogen gas present in the sample. So, what I get to do is a PV equals nRT. But the pressure I use is not 0.810 atmospheres, it's 0.810 minus 0.0237. So, whoops. I might just do it on the side. 0.810 minus 0.0237 equals 0.810 minus answer. So I have 0.786 times the volume, which is 1.7 liters. That's given. Liters is a good R unit. R is 0.0821, which of course is a good R unit. And the temperature is, it doesn't give me a temperature. So I'm going to assume that the temperature is 25 degrees Celsius because that's standard room temperature. So let's call that not 25, boo, but 298 Kelvin. And let's hope we get an answer here. And if we don't, well, oops. And if we don't, we'll just pretend it's there. So to solve for moles, I would take 0.786 times 1.7 divided by 0.0821 divided by 298, which I wrote incorrectly a dozen times, and N is 0.05, oops, yeah, 0546 moles. Close enough. Okay? And we get this happy thing because we remembered to subtract, like Dalton's law of partial pressure. 15 we're going to do in class. I'm sorry I kept it here. It was just attached to the previous one. So we are going to do 15 in class. It's quite nasty and long. Diffusion and effusion. I'm sorry, I called diffusion and effusion. Diffusion is spreading out. Effusion is leaving through a hole. Formula is based on molar mass, and the formula is rate 1 over rate 2 equals the square root of molar mass 2 over molar mass 1. And please look up your VRMS formula. We talked about it in class a little bit. It's the square root of, I can't remember, something or other. But look at that and put that in your notes right now. Pause it. Go put it in your notes right now. Don't be surprised that's a podcast question. What is the formula for VRMS from your equation sheet? Excuse me. So, here we go. Hopefully. Calculate the ratio of effusion for the rates of N2 and N2O. So this is number 33. So R1 over R2 equals, actually I'm going to call this RN2 and RNO. That way I can keep track of it. Square root, and remember it's inverted. So the molar mass of NO is 16 plus 14, which is 30.01, and 28.02. So 30.01 divided by 28.02. Enter. Second answer is 1.03. So, oh, what did I do wrong? The ratio of the fusion rates of N2 and N2O. Oh, N2O instead of NO. That's what I get for not being literate. So it's going to be the rate, so it's going to be square root of N2O, which is 28.02 plus 16. So 44.02 over 28.02. So second root that, and I get quit go to. So second root 1.571, 1.25, which would be C. The diffusion of a gas is faster than the effusion of a gas. False. Rate's the same. Particles are moving in the same direction. They don't slow down for those things. It's not like line up. Remember, gases don't want to effuse. They just happen to effuse. Ideal gas with corrections. Van der Waals came up with the corrections for the ideal gas law to make it work with all gases. By the way, the N here equals moles. So we've got all these mole things all over the place. The equation, the AP problem, got rid of the N on one side and made it all funny. But basically, you have to know what B and A stand for. B, again, is a big ol' volume of the particles. So B stands for volume of particles, not as a group, individual particles. Individ. And A stands for attractions. We like to ignore the attractions, but they're there. Kind of like we like to ignore our girlfriend's friends, but they're there. So looking at this again, particles really have volume. Oh, this just goes over the same thing again. So look at that if you want to. Let's do the last couple of problems and be done with this. Ooh, the Van der Waals equation. nRT equals blah, 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 incorporates to the ideal gas law in order to account for the properties of real gases. One of the corrections accounts for the possibility of chemical reactions. No, 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 no. The only thing we have is big old volume and attractions. The finite volume of molecules. Finite means measurable. True. The quantum behavior of molecules. Woo! I'm going to put question mark, although the answer is no. The fact that average kinetic energy is inversely proportional to temperature. First of all, it's not, but who cares? That has nothing to do with big old volume or attractions. The possibility of phase changes when the temperature is decreased or the pressure is increased. No. It's just B. Yay. That was 35. 36. Which of the following properties of a real gas related to the B coefficient of the Van der Waals equation? Big old volume. Real gases consist of molecules or atoms that have big old volume. It's a big old volume. That's a big old A. That's what I'm going to get on this worksheet. The average speed of molecules? Nah. Their attractive forces? Nah. The rate of effusion? Nah. And we're all done. All done. Yay. Sorry I skipped 15. It's long and annoying, but it's the first thing I'm going to do in class. And we get out of here with under 20 minutes of podcasting. Woohoo! So be sure to enjoy yourselves tonight.